let's take a quick look at some spectroscopy of ethers, at least. We won't talk too much about the sulfur compounds in their spectroscopy, but ethers are not tremendously visible on IR because the only thing you could see on IR possibly might be a CO bond, but that would be from 1050 to 1150, and there's dozens of other things that could be in that range. So that's not necessarily instructive to us. We can, of course, use the absence of other things, like the absence of a carbonyl or the absence of an OH, if we needed to figure out something's in ether. NMR is going to be most useful for us, obviously, with ethers. The H's on the carbon next to the O. So here's the carbon next to the O, and its H's. Those are going to be the most strongly de-shielded. So between 3 and 4, right? 3.5 to 4.5, because they're closest to the O. That brings them furthest to the left on the NMR spectrum. So in this case, it's symmetrical, right? This is di-N-propyl ether, but it's symmetrical, so we only see 3 resonances. This one here is just a blow-up of the one next to it. Mark that like that. But you should be able to look at the multiplicity of these peaks here. The ch2 that's furthest away has 2 hydrogens next to it, so that's a triplet. That's 2 hydrogens high, right? Its integral right there is 2 H's. The green ones here have 1, 2, 3, 4, 5 next to them, so it's actually going to show 6 peaks. It's a hextet or hextuplet or something like that, and it is 2 hydrogens high. Finally, the CH3 has 2 next to it, so it's a triplet, but it is 3 H's high. So I think a spectrum like that is simple enough that it could be that could be an example of an exam type question, I think. Epoxides are a little less shifted than normal ethers are, just because of all that ring strain that brings a little extra electron density in around them where there normally wouldn't be any. So CH2 here, right, and the other CH, they're going to be pretty similar to each other. The CH2, though, right, attached to the epoxide, notice that has actually 2 peaks. That's because each of those hydrogens has its own peak. Like I said, if I sort of draw this epoxide from the side, there's 1 H up, 1 H down. On the other carbon, there's a CH3 up and an H down. Notice this carbon right here is a chirality center, okay, 4 different things attached, so that these two different H's have 2 different relationships to that CH3. One is sort of right next to it, one is way across from it, right? 1 H is cis to the CH3, one is trans to the CH3. Okay, so different chiral environment due to their chirality center that's right next to them. That can actually make a pretty big difference in a small molecule like this. Notice the CH3 here is a doublet, just like we would expect, because it's split by the 1 hydrogen to the next, right next to it. CH is going to be a complex multiplet, as well as the CH2s themselves. So I would not expect you to be able to analyze the complex multiplets in there. The doublet should be not surprising to us. Doublets and triplets and quartets and things like that should be familiar to us too by now. So that's it for this chapter.